Since I was asked a lot, I'm going to show you how to create this Breath of the Wild styled animated grass shader. So we are going to split this up into 4 steps. In the first one, we're going to create the wind shader. This is going to tell us how we should deform our grass mesh at the specific point of space. In the second step, we're going to create the grass geometry, just a single blade of grass. And in the third step, we will use instancing to actually populate our patch of grass. And then we are going to put it all together. Okay, let's start with the wind shader. We're going to need a bit of geometry so we can preview the shader as we work on it. So let's create this ground mesh and let me align it with the Y0, just like this. Okay, and let's create the shader material and save it right away. It will be a bit easier to manage this later on. And let's do the same thing for the shader itself. Let's call it wind shader. And we have to define the shader type. In this case it will be spatial. And let's create fragment function just to test if that indeed works. Okay, we have to define the noise function, which is going to tell us how much force we need to apply to our grass mesh at the specific point of space. And for that, we'll be using the whirly noise. This is rather simple but very useful noise type, which for every P we supply and some arbitrary set of points is going to find the minimum distance. And let me show you how we're going to calculate it in this very simple predefined sample, and then we will turn it into something more manageable. So let's define a couple of points like this. Let's see, maybe something in the middle. And we're going to need reference distance, which starts at 1.0. And let's step through our array. And for every point, let's update the distance of minimum between distance and length of difference between P and the point we are testing. And we return the distance, and all we have to do is call it right here. And let's test with UVs. And here you go. So the problem with this code is that we are using only 3 points, and if we want to cover some large area, this is not enough. But also, if we would like to pass some variable number of elements, we cannot do that because in shaders our loops need to have predefined number of steps. Basically, you cannot have this as a variable. And this creates a problem for us. Fortunately, smart people have figured out the way around this. And what we need to do is tile our noise. So through the simple multiplication, we have created a grid. And now if we modify the code and ensure that in every cell of this grid there is only a single point, we can then modify the loop so it steps over this 3x3 region and calculates the minimum distance out of it. We are not going to need most of this function anymore. We will remove all those pieces. And the first thing we need to do is split our p into the integer portion of it by taking the floor, and we need the fraction portion of it. And obviously we'll be using fract for that. Let's ignore the integer part for now. Let's create our loop, which is going to step from -1 to 1 on both axes. Now we need to actually convert this into vector 2 and we can calculate the diff. And this is the place we're going to put our reference point for the cell, but we don't have this data, and let's predefine this as the middle of the cell for now. And we have to subtract the fraction of p. And again, we're updating the distance by taking the min of dist and length of difference. Okay, so it's more like it. So the only thing left to do is to replace this reference point in the middle of each cell with some randomized point based on the cell index. So we have to create a random function that is going to return random point in the range between 0 and 1, and we will input some kind of p vector. So one way to do it is to use dot products, and I'm going to write it real quick and explain what am I doing here. So we want to take the dot product between p and some arbitrary vector. For both axes. And taking the dot product between some p and some other vector, and in mind these are not normalized, these are not the unit vectors. So we get some number out of this. It's not going to be in the range of -1 to 1. It's going to be some number. And to wrap it up into this range of -1 and 1, we need to take sine of each axis. But obviously this is still not in the range between 0 and 1. And to do that, we take fraction out of it, and fraction is always positive number. What we can do more is to create some kind of offset for the sign, but you know, we don't have to do that. And now let's plug our random function here, but instead of using this predefined point, we are going to take our integer portion of the p and let's add n to it. Okay, and this randomizes our points. And now we can actually animate this if we add time multiplied by some direction like this, And this is basically our wind function here. With the wind shader ready, let's look at the grass geometry. And for that, we'll be needing only a mesh for a single blade of grass. And we could prepare this blade of grass with Blender or something, but you know, let's do it in a geeky way and create the script. So let's call it a mesh factory, and this mesh factory is going to extend the object and expose static function simple grass. This will return the mesh object. And we'll be using array mesh to construct it, and for that we need to prepare arrays of all values per attribute we're going to need. So we obviously need vertices, so pull vector 3, and also UVs. Well, not really. We need a place to store a parameter that is going to be used to decide how much of wind influence we're going to apply to a single vertex. You see, we want only the tip of the grass blade to be affected by the wind. We don't want the base of the mesh to be affected at all. And our mesh will be very simple in this case. We could create something more complex, but we don't really need to. We'll be making a single triangle. And let's predefine all the points, since this is very simple triangle, nothing more. And since we start with the base, our UVs here will be at 0. Unfortunately, there is no other attribute with that takes less amount of memory. We cannot have like single float here. And the second point of the base, again, UVs here will be 0 and 0. And now we need to define the tip. So the tip will be right in the middle, like this. And okay, this should be pushed back. And at the tip we're going to have full force of the wind. Okay, now we need to compose our arrays into a master array. This array needs to be reformatted, resized to fit all the attributes, all the channels. And we need to pass our vertices, and we need to pass our UVs, and we can either do it as pass it as UV or UV2. Let's use UV2 because it seems like a bit more appropriate. And array mesh, and we need to add surface from arrays and primitive triangles, since this is like only one triangle. And let's set the custom axis aligned bounding box. So we need to define the min and max position here. So this is rather simple. Let's do something like that. And something like that. Sorry. Okay, and let's return our mesh. And this is basically it. Our mesh is ready. Now we can actually do the instancing part. So with the mesh factory done, let's plant some grass. Let's create another script, let's call it planter. And for this node we'll be extending multi-mesh instance. Let's remove all of this. And I want this to work in editor mode, so let's define it as tool. And we need to set up some properties for the inspector. We're going to need size of our grass patch. Let's call it span, and let's predefine it to. We also, for every property, we're going to define setter methods, so we can actually update our instances. We're going to need also the count of our blades. 1k should be okay default parameter here. Again, we need setter function method. And next we're going to define a couple of properties that will be used to randomize the grass patch a bit. We'll be setting width as the range between some min and some max. The vector2 is just a data structure to hold it. We would have to create another data structure just for that. It doesn't make sense. Let's use the vector2 here. Set width and same for height. Maybe something like that. It keeps complaining about the setter functions not defined, but don't worry about it. And apart from width and height, we are going to define sway angles. So the grass doesn't move in exactly the same way. So it adds a bit variation to the grass movement. Set get, set sway. And the same for pitch. It can be also 10 degrees. Okay. So before I define the setters here, I will create the empty rebuild method. It's not going to do anything at the moment, but we will call this method in every time we need to update the instances. So on the init, on ready, and also for every setter method. So let's start with span. Just like that. And I will repeat the process for all the other properties here, but I will fast forward it because it's like super repetitive. No point in you sticking around. Okay, we are ready to fill our rebuild method. And the first thing we need to check is if the multi-mesh object exists. This is where all the instance data are stored, and if it's missing, then we're going to crash. And also let's make sure that no instance data is carried over from the last rebuild. So by setting instance count to 0, it clears everything. Now we need to set up the mesh we'll be using for instancing, and yes, this is the moment we need to use our mesh factory. We're going to preload it. And since its method is static, we can just use it without instancing the factory itself. Okay. Next, we need to set up the data format for our instances, and the first one is transform format, which is obviously 3D, and we need to do this before we actually define even the number of instances. We need to set it up before we do anything else. We're going to need also the custom data format. This will be used to store the blade of grass size, angles, and so on. And we can also use colors, but we are not going to need that here. Okay, and now we can set the instance count to our count. Okay. And now we can step for every index in range between 0 and multi-mesh instance count. We're going to need position or origin for our blade of grass, and let's use round range, and let's use minus span plus span. For y it will be 0, and z will be also random. Next, we need to set up the rotation, and it will be simple. We'll be using the word up vector, and we need to convert to radians and again randomize between 0 and almost full circle. And now we can set the instance transform, and we need to pass the index and the transform, which we get from we created with basis. And the last thing we need to set is the custom data structure, and we'll be using color for that, but again, this is like a color has 4 flows and we need to pass 4 flows, so this is why we're using color. And first, let's pass the width of our blade of grass. Then let's pass the height. And then the angles. And you can do it in every order you want, as long as you receive it in the exactly same order, interpret it in the same order on the shader side. and exactly the same for yo. Okay, seems about right. Just don't forget to save. Okay, let's test it out. And we have to create multi-mesh instance. Let's call it grass. And we need to assign our planter script. And as you can see, it kind of works. It doesn't look like grass yet, but the planter does what it should. And once we actually set up the material and the shader in the next step, we'll be done with it. Let's create grass material. And we have to assign it here in the material override. And this will be shader material. Let's save it right away. And let's do exactly the same thing for the shader. The shader type will be spatial, and the first thing we should fix is a scale problem. At the moment, every blade of grass is rendered with this same width and height, which is too large, and this doesn't look anything like patch of grass. So let's copy the current vertex data from this built-in variable. And let's scale the vertex by instance custom data. And at the end, we have to reassign it to the built-in variable. So this instance custom structure, this is the representation of custom data assigned here in the planter script. So this becomes X, Y, Z, W. And it is accessible through this instance custom structure. If you look closely at this mesh, you will notice that the blades of grass are rendered one-sided at the moment. So let's correct this right away. We can do this in the material, or we can set up the flag right here, and this will be cool disabled. So now you can see that grass is rendered with both front and back. And another thing that is missing in our mesh is the normal. So because we are making the stylized grass, we can assign this up vector like this. And as you can see, it doesn't work 100% correctly as we would expect. So some of these blades are rendered with exactly the same color as the ground here, which is correct, but other blades are rendered incorrectly. And the reason this happens is that when you render the two-sided geometry and you render the backside, the normal gets reversed. So if I reverse it like this, you can see that we are reversing the normal, so other half of them is rendered incorrectly. So to fix that, we have to use front-facing variable. This tells us if we are rendering the front or the back of the mesh. But this variable is either 0 or 1, and we actually want this either +1 or -1. And all we need to do is multiply normal by this. And as you can see now, every blade of grass is rendered with exactly the same color, which obviously makes it hard for us to see anything. So let's add two colors that we are going to blend together across the blade of grass. And let's make the top color white and the bottom color black. And here inside the vertex shader, let's compute the final color by mixing those two. And we'll be using for that the wind influence parameter. This comes from our mesh factory. These properties we put here in the UVs. So all that we need to do now is to output the albedo like this. Looks good, but of course we need to assign some real values, and since we have defined these as the uniforms, we can simply set the parameters here, and I have already preset 2 shades of green. We want some lighter shade and some darker shade for the bottom. And to make it blend correctly with the floor, let's create new material here, and in this case we can use default spatial material with just albedo set to the darker shade. It looks a bit dark, so let's create environment, perhaps some kind of sky, and let's ramp up the ambient light energy. Okay, seems about right. So I guess this is a good moment to port our wind function from this shader we have created previously. So all we need to do is copy the whirlay and the random function, and here in the wind shader we used to pass the UV space in the whirly function, but here in the grass we cannot really do that because our geometry is instanced and it doesn't share the single UV space. Fortunately, there is a way around this. We can kind of calculate the UV here from the word position of the vertex. So let's create the UV variable and let's multiply the word matrix with the vertex position, and we will pass here -1, otherwise our noise will flow in the opposite direction. And let's extract X and Z here. So now if we comment this out and instead we will compute the whirly for our UV, And of course I forgot that this needs to be color 4. So let's correct this. And wind, and 1.0. I can see that it works, but to make it more apparent, let's raise it to the power of 2. And yes, this seems to be working. We could actually also test if it animates, and perhaps we could increase the scale of our whirly noise like this. This will make it tile more. And to animate this noise, we have to define a couple more parameters. So actually let's turn this into wind scale. Like this. And let's define the wind speed, and we also going to need wind direction vector 3 in the word space coordinates, and we will make it flow in forward in the word space. And one more thing, we are not going to modify the Y component here. This is going to make our calculations more much simpler. And since we are going to input the wind direction manually, let's compute the wind direction normalized. And let's compute our scaled time like this. And all that is left to do is to add to the UV our wind direction normalized XZ, because we want like 2D plane here, multiplied by time. And as you can see, the whirly noise is animating. It moves over our patch of grass. Okay. And one more thing we are going to need is a utility function that is going to compute rotation metrics for us from axis and angle, rotation around an axis. And for that we'll be using something called Rodriguez formula. But the math behind this formula is way beyond the scope of this video, so I'm going to fast forward this part. But the takeaway here is that this matrix is representation of rotation. So when you multiply any vertex or any vector by this matrix, it's essentially like you would rotate it. And we're going to need this because first we're going to rotate our blade of grass towards the direction of the wind, and then using the wind power we have calculated, we're going to bend this blade of grass towards that direction. Okay, and let's test it out. I'm going to define rotation axis, the default one. Default ones here is not really required, but it's more tidy this way. We need up and right hand axis. And what we can do is rotate the vertex around the y-axis, up vector. So our vertex will be calculated with this function we just created. We're going to use up vector and multiply by vertex. And as you can see, the blades are rotating around y-axis. I'm going to replace this one, and we can remove these test lines. I'm going to define the sway angles, and these are going to control how much our grass is going to deform. Let's see something like that. Sway yaw, 45 degrees, and so these are like the base value for the material, and here in the planter we have created these two values that will be kind of to make each blade move in the kind of unique way. And since these are in the degrees, we need to convert to radians. So we have to define the pi, which is a bit weird. Godot should expose these for us, but you know, what can you do? And all we need to do is multiply our degree angle by this, and this is going to give us the same angle in radians. And since I am already here, I'm going to define varying float wind. This will replace our wind variable down below. This is because I want to use the wind power in the fragment shader to add some final touches, but without the wind it will be impossible. Perfect. So now let's make sure that our wind force is scaled by our wind influence factor encoded in the UV2. Now we have to transform our world space wind direction to the model space, and for that we're going to inverse world matrix, and we're going to compute wind forward in the local space by multiplying wind direction normalized, and to get the right hand vector we're going to take cross product out of wind forward and word up vector. This is why I didn't want to touch the Y component in the wind direction. Otherwise, this will be more complex. And now, since we have the rotation axis, now we need to calculate rotation angles. So let's calculate the sway pitch first, and we're going to take degree sway pitch, convert to radians, and we're going to multiply by wind power, and at the end we're going to add instance custom Z. This is the default value we have passed in per instance data. And for the sway yaw, this other sway is going to wave aggressive blade back and forth. We need to again calculate the sway yaw deck, convert to radians, now we're going to multiply this by sine of time and multiply by wind power, and at the end we're going to add the instance custom W. Okay. Now all we need to do is calculate the rotation matrices. So let's start with the bending the blade of grass forward, and we're going to use our axis angle function. The angle is ready, and the axis here is wind right, and the other rotation will be rod forward, and again our utility function, and this time will be sway yaw and wind forward. Perfect. So now here we are scaling our vertex, and the last thing we need to do is multiply rotation right multiplied by rotation forward multiplied by vertex, and this should be it. And as you can see, the blades of grass are moving, and I guess this is a good moment to add the final touch. We'll be using the wind we have already calculated up here. So let's keep the specular at the 0.5, and let's calculate roughness by clamping. To wind between 0 and 0.0, something like that. And all that is left to do is to adjust the parameters. Let's increase the density here. Oh yes, oh yes. So thank you for watching. I really hope you have learned something today, and if you can't live without the project files, you can find the link in the description below. Have a great day and see you next time.